Hello everyone, so this is going to be a GCSE Combined Science Trilogy past paper walkthrough. This is Chemistry Paper 2, Foundation Tier, that was sat in June 22. Okay, so I'm going to model it as I would have tackled this paper, and I'll put links at the bottom if you need a Cognito revision video on any topics that you're maybe not as secure on. So, question 1 then. This question is about the Earth's atmosphere. The Earth's atmosphere contains 21% oxygen. Draw the bar for oxygen on figure 1. Okay, so you need to know your scale. You've got, it's going up 20 to 40, so you've got a gap of 20, and you've got 10 squares. So 20 divided by 10 is 2, so each little square is worth 2. So that means if I want to draw a bar for oxygen, which is 21% oxygen, it's going to literally be halfway between, just fractionally above 20. You've got to try and get it bang in the middle between 20 and 22. Okay, so you've got to try and be as accurate as you possible using a ruler, making sure it's in between those two lines, and that would get you 1 mark. What is used to test for oxygen gas? So this is one of our gas tests. Well, to test for oxygen gas, we use a glowing splint. A glowing splint will relight in oxygen, and it will then become a full burning splint again. A burning splint is used for hydrogen gas. That's your squeaky pop test. Litmus paper is used to test for chlorine gas, and lime water is used to test for carbon dioxide. Okay, so you've got to know what piece of apparatus we use for each different gas. The Earth's early atmosphere was very different to the atmosphere today. Figure 2 shows the composition of the Earth's early atmosphere and of the Earth's atmosphere today. So you've got the information here. You've got 95% CO2, water vapour and small amounts of nitrogen, and then today 78% nitrogen, 21% oxygen, and then small amounts of carbon dioxide. The percentages of nitrogen and oxygen in the Earth's atmosphere today are different from the early atmosphere. Complete the sentences using the figure 2 and using the words from the box. They can be used once, more than once, or not at all. Since the Earth's early atmosphere, the percentage of nitrogen in the Earth's atmosphere has, well, if we look in the early atmosphere, we had small amounts of nitrogen, now it's 78. So it's obviously gone up. So it is increased. Since the Earth's early atmosphere, the percentage of oxygen in the Earth's atmosphere has, if I go back to the diagram, oxygen isn't even noted on the early atmosphere, but now we've got 21%. So it's obviously got bigger again. So again, it's increased. The Earth's atmosphere today contains a small amount of carbon dioxide. Why has the percentage of carbon dioxide decreased since the Earth's early atmosphere? So basically, where's all that carbon dioxide gone? Well, it's actually the first 2 boxes. It's dissolved in oceans and used in formation of sedimentary rocks, like calcium carbonate. Industrialisation, that would have released more CO2, respiration releases CO2, and volcanoes release CO2. So that would have actually caused it to go up, but the top 2 have caused the amount of CO2 to go down. Oxides of nitrogen are produced when nitrogen reacts with oxygen in car engines. Figure 3 shows the concentration of oxides of nitrogen in the atmosphere during 1 day in a city. Okay, which 2 times have the highest concentration of oxides of nitrogen in the atmosphere? So you're just looking at what 2 times are the 2 peaks. Looking carefully, so you've got 9 AM, and then the next time would be 5 PM. Suggest why there are the highest concentrations of oxides of nitrogen at these times. Well, we know it's to do with car engines. We've been told that in the question. So it could just simply be there are more cars on the road at these times. Okay, generally peak traffic out time. Right, question 2 then. This question is about fuels. Coal deposits were formed by the remains of dead trees. Name the process in which the leaves of trees that uses carbon dioxide. So what is the process in the leaves that is using carbon dioxide? Linking to a bit of biology here, it is photosynthesis. That's what happens in the leaves. How is coal formed after the trees die? Okay, well, the trees, if they're burned, that wouldn't turn it into coal. That's not that. The trees aren't melted, they are generally compressed. They get buried, and that's where we find the coal buried underground. It's buried by all the sediment that forms on top of them. Coal contains small amounts of sulphur. Name the gas produced when sulphur burns in oxygen. So it would be called sulphur dioxide. Okay, like carbon reacting with oxygen makes carbon dioxide. Sulphur and oxygen make sulphur dioxide. Give 2 problems caused by the gas produced when sulphur burns in oxygen. Well, you've got to know sulphur dioxide is the gas that causes acid rain. Okay, that would be 1 mark. You could also say acid rain causes damage to buildings. The other thing you can say is it causes respiratory problems. Question 2.5. Figure 4 shows the relative amount of electricity generated from different fuel sources in the UK from 2012 to 2018. Describe what happens to the amount of fuels used to generate electricity in the UK from 2012 to 2018. So 3 marks. What has happened to the different amounts of the fuels as the years have gone on, but specifically 2012 to 2018. So let's take each bar at a time and just describe. Describe just means say what you see. So what's happening to our fossil fuels? The blocks at the bottom. Well, the fossil fuels we can see are decreasing. So that's like my first point. Fossil fuel amounts used are decreasing. What's happening to my renewable sources? Well, I can see my renewable sources are getting bigger. Renewable sources are increasing. Nuclear, I can see, has generally remained quite stable or constant. So nuclear is constant or not changed. Okay, and the same thing for other. So you'd say other sources have not changed. Okay, so that's question 2. Question 3 then. This question is about ammonia and its compounds. A student heated a sample of ammonium chloride. The equation for the reaction is given below. One product is ammonia. What is the name of the formula of HCl? So you've got hydrogen and you've got chlorine. So when you've got hydrogen and chlorine bonded together, it becomes hydrogen chloride. But you are also allowed to say this is the formula of hydrochloric acid. So that would also be accepted as well. Ammonia is a gas. What is the state symbol for ammonia? Well, you've just been told it's a gas, so which one is most likely to be a gas is obviously G. How does the equation show the reaction is reversible? Well, it is just the symbol with the 2 half arrows. This is our reversible reaction. You could just say it has the symbol of the reversible sign and draw it out. Draw out the symbol. The forward reaction is endothermic. So therefore the reverse reaction is basically saying what's the opposite of endothermic? Exothermic. Okay. And then last one, choosing the word from the box. Equilibrium is reached when the forward reaction and reverse reactions happen at exactly the same rate. So remember, this is rates of reaction. It's basically the speed of a chemical reaction, how much you're making a certain amount of time. If you are at equilibrium, things are equal, your forward rate is equal to your reverse rate. The industrial process to produce ammonia uses a catalyst. Figure 5 shows a reaction profile with and without a catalyst. Which letter represents the activation energy for the reaction with a catalyst? So you should remember that activation energy is the bump. It's the size of the bump that you've got in a reaction profile. But which one is with a catalyst and which one is without? Well, what we should remember is that a catalyst reduces the activation energy needed. So therefore, a catalyst is likely to be C because it's reducing the amount of activation energy needed. With D, if it didn't have a catalyst, those particles would have to have a lot more energy in order to react. But with a catalyst C, the activation energy gets lower. 3.7, give one reason why using a catalyst reduces costs, but do not answer in terms of activation energy. So you've just got to think about catalysts. Why does industry use them? But what do they do? You should know a catalyst increases the rate of a reaction. So therefore, it's just generally quicker. And therefore, you could also say, because less activation energy, it can be done at lower temperatures. And that also saves energy as well. Ammonia is a mixture that can be used as a household cleaner. What is a mixture that has been designed as a useful product called? So you've got a mixture that's been designed as a useful product. Now this is just one word that you need to be aware of, and it's called a formulation. So it's like paint. Paint is a useful mixture of different things mixed together, and the fancy word for it is just a formulation. It's literally one line on the specification that you've just got to be aware of. Question 4 then. A student investigates the effect of the concentration on the rate of reaction between sodium thiosulfate and hydrochloric acid. Figure 6 shows the experiment. The experiment was done in a fume cupboard. So you've got sodium thiosulfate and hydrochloric acid. You've got your black cross drawn on a piece of paper and a timer. This should be a practical that you remember doing. It's quite a classic one, and everyone seems to remember it. This is the method used. You pour 50 centimetre cubed of sodium thiosulfate into a conical flask. You put on the conical flask on a black cross drawn on a piece of paper. You pour 10 centimetre cubed of hydrochloric acid into the conical flask and then start a timer. You stop the timer when the cross can no longer be seen. You repeat the experiment with different concentrations of sodium thiosulfate solution, and then you would see the difference. Draw one line from each type of variable to the correct example of the variable in the investigation. So you've got dependent and independent. You should remember dependent is what you measure, independent is what you change. So if I start with what I'm changing, what am I actually changing in this experiment? Well, it says it at the bottom of the method here. Repeat it with different concentrations. Independent then would be our concentration. The dependent variable is what we are measuring. What am I actually recording in my results table here? Well, I'm not recording the temperature of the solution. I'm not recording the amount of acid or the volume of the flask. I am recording the time taken for that cross to no longer be seen. So that is my dependent variable. Question 4.2. The experiment is done at room temperature. What is the temperature shown on the thermometer in figure 7? So it's literally, you can see here, the line is halfway between 19 and 20. so it should just be 19.5. Then, table 1 shows the results, and you've got the time in seconds. And then, obviously, it says, plot the data from table 1 onto figure 8 and draw a line of best fit. You can see they've given you the axes and it's all labelled, so that's all fine. You don't need to do that. It's just literally plot the data. But what you need to do is make sure you understand what your scale is. You've got a gap of 20 and you've got 10 little squares. So 20 divided by 10 is 2. Each of these little squares is worth 2. And then your concentrations, I believe, are just going up in 0.1s anyway. So 0.1 is 82. So go to 0.1, one little square above 80 would be 82. And you've got to be within half a square to get the marks. So 0.1 is 82, 0.2 is 40. So that's easy, that's bang on the main line. 0.3 is 20. 0.4, you could tick it off as you go. 0.4 is 13. So 0.4, you'd go to 10. 12 would be here, so 13 would be halfway in between. 0.5 is 10, that's easy, halfway there. And then 0.6 is 8, so there. And then you need to draw your line of best fit. What I would actually do is move your paper and with your hand to make it easier, and it's obviously going to be a curved line of best fit. Remember, in science, you want to try and aim and do it in one smooth line. Okay, don't do a line of best fit like shading it and colouring it like that. It should be one smooth line. Okay, so just make sure it's as smooth as it can possibly be. Predict the time taken for a cross to no longer be seen at a concentration of 0.7 using your graph for figure 8. So at 0.7 you can see we haven't got any data. But what we can do with our line of best fit is extrapolate or extend our line of best fit. And as long as you extrapolate your line of best fit and then read off the value that you think it would be based on your results. So I go up, then I go across to my y-axis. I can see I'm 3 little squares up. Obviously you would use a ruler. That would be about 6 seconds. Okay, so I'm extrapolating using my line of best fit. Complete the sentence. As the concentration of thiosulfate solution increases, the time taken for the cross to no longer be seen, or what's happening, what to our time, is going down. So it's decreasing. Okay, so you would just leave it as just by saying decreases. Question 4.6. In one experiment, 0.725 grams of sulfur is produced in 20 seconds. Calculate the mean rate of reaction from 0 to 20 seconds, and it gives you the equation to use. So the mean rate of reaction is the mass of sulfur produced in grams divided by the time taken. So it's quite simple, you're just substituting in the values. 0.725 is your mass of sulfur, and your time is taken 20 seconds. So 0.725 divided by 20 would then give you 0.03625. Now, if you get to that actually in this question gives you 2 marks. It hasn't asked you for the units. But if you did want to put the units on, which it sometimes asks, well, it's grams per second. So you just put G/S. Oh, in fact, if I look ahead, that is the next question, G/S. Okay? Right. The student did the experiment with 0.15 mole decimeter cubed sodium thiosulfate solution and repeated it 3 more times. Calculate the mean time of the reaction, but it's told you do not include the anomalous result, and give your answer to 3 significant figures. So an anomalous result is the result that is a weird result, or one that doesn't fit the pattern. Which of these tests doesn't really fit the pattern? Should be quite obvious. It should be test 3. That's significantly different. The other 3 are quite close together. Then you would do your normal mean calculation, 60.5 plus 63.2 plus 65.7, divide it by 3, and that gives you an answer of 63.13 recurring. Now you want it to 3 significant figures, so you would draw your line after 3 figures, and because it is a 3, you would round it down, so it would just be 63.1. If you left it at 63.13 recurring, you would only get 2 marks, because you haven't quite finished the question. Okay, so that is the end of question 4. Okay, so question number 5 then. This question is about hydrocarbons. Figure 9 shows a hydrocarbon. Complete the formula for the hydrocarbon shown in figure 9. So we just simply need to know how many carbons we've got and how many hydrogens we've got. So just by looking at it, it's C3H, count them all up, and it's 8, C3H8. What is the name of the hydrocarbon in figure 9? Well, you've only got to know the names of the first 4 hydrocarbons. If it has 1 carbon, it's methane, 2 carbons is ethane, 3 carbons, like this one, is propane. So meth, eth, prop. And if you had 4 carbons, the last one you've got to know is called butane. So methane, ethane, propane and butane. Because we've got 3 carbons here, it's propane. What homologous series does the hydrocarbon in figure 9 belong to? Well, homologous is just homologous series is just a fancy word for saying what family or what group do these hydrocarbons belong to, and it's the main one you've got to know in combined foundation, which are your alkanes. Okay. 30 grams of another hydrocarbon contains 24 grams of carbon. Which calculation gives the percentage of carbon in the hydrocarbon? So before I even look at the answers or potential answers, I would be thinking, right, if I was typing it into my calculator, I want to find the percentage of it, I would be doing 24, which is my grams of carbon, out of my total, which is 30, and then I would be timesing it by 100. And I would be seeing which one is closer to that. Well, the first one, 24 times by 30, no, that's not correct. Second one, you've got 100 times by 30, and then divided by 24. That doesn't seem to be the right way. The third one, well, I've got 24 and over 30, and 24 is times by 100. Potentially, just double check the bottom one. 24 over 30, it wouldn't be 30 times by 100, because that would be 24 over 3,000, so it wouldn't be that one. So therefore it would be the third one, which is the closest one to that. Table 3 shows the boiling points of some different hydrocarbons. Describe how the boiling points change as the number of carbon atoms in the hydrocarbon increases. So as my carbons are getting longer, what's happening to your boiling points? Well, I can see if I'm increasing the number of carbons is increasing the boiling points. Okay, so as my chains get longer, the boiling point increases. Hydrocarbons can be cracked. Give one condition used to crack hydrocarbons. Now, you should remember cracking is when we've got a long chain hydrocarbon or alkane and you crack it into 2 smaller ones. And you normally make a shorter chained alkane and an alkene. One condition, basically what do we do to crack it? You could either heat it up or use a catalyst. So heat or catalyst. You've then got to balance the equation for the cracking of C6H14. So it's balancing equations, but I know it's only 1 mark, so therefore it should be relatively simple. Okay, now we've got 6 carbons here, and we've got 2 carbons, so if I divide it on my reactants and products, I've got 6 carbons here, but I can see I've only got my 4 carbons on my right hand side. So therefore, in order to balance it, I need another 2 carbons, and this is what I would normally do on a foundation paper if I've got a balancing equation question. If you're not sure, put a 2. That would mean I've now got 6 carbons. I can check my hydrogens. I've got 14 hydrogens. I've got 6 hydrogens here on my left hand side, and I've got 2 lots of 4. That gives me 8 hydrogens. If I add 8 and 6, that gives me 14. So I know that is right. Give one reason why hydrocarbons are cracked. Well, hydrocarbons are cracked to make smaller chains. Okay, so we get the long chains and we crack them to make smaller ones. That's actually enough to get the marks. But if it was a 2 or 3 marker, I might also add on to make smaller chains as they make better fuels. Remember, the smaller chains are more flammable, more combustible, and therefore they make better fuels. Question 5.9 then. Window frames can be manufactured by wood or plastic. Table 4 shows the results of a life cycle assessment for making one wooden and one plastic window frame. Give 3 advantages of using wood instead of plastic in the manufacture of window frames. So it's 3 marks and you've got 3 points there, and you just need to look at the table and you see which one is better for wood. Now, in terms of total energy used, well, I can see the wooden frame is actually lower than the plastic frame. So that's an advantage. Okay. Crude or coal and oil used in kilograms, I can see a wooden frame is using lower amounts than a plastic frame. So that is also good. The waste is also lower than a plastic frame, 16 to 28. However, the cost is actually more expensive. So therefore, I would have to stick with these top 3 here. All I would say is, you can do this really precisely, uses less energy, uses less coal and oil, therefore less greenhouse gases, etc. And therefore, and you can also say, produces less waste. Okay, really, really simple question there, just interpreting a table. Question number 6 then. A student investigated the colours in brown ink using chromatography. So hopefully you remember chromatography, this required practical. Give 2 errors made by the student, so they've obviously set it up wrong, and describe a problem each error would cause. This is a classic question. What do students do wrong when they do chromatography? Looking really carefully at the diagram, look at the labels. I can see the start line is drawn in ink, and I can look where the solvent is. Normally, it's always these 2 mistakes that they put every single time. So for error 1 is the start line is drawn in ink. That is a mistake. And then you've got to say the problem that it will cause. Well, if I've got my start line drawn in ink, it will mix, or the start line will mix with the solvent, okay, and mess up and basically contaminate the results, okay. What should be done, it should be drawn in pencil, because pencil is insoluble. Error number 2 is that our solvent front is actually above our start line. So what would happen is that all of the ink would then basically wash off into the liquid, into the solvent, rather than rise up the paper. So error number 2 is the solvent line is too high. And the error of that is, so the colours will dissolve into the solvent. So they would dissolve in the solvent and not rise up the paper. A student set up the apparatus correctly, okay, and it says to give 2 conclusions the student can make from figure 11 about the 4 colours in the brown ink. So there are different things that we can say here about the 4 colours in the brown ink. Remember, if the dots have gone up to the same level, for instance here, you can assume that they are the same substance because they travel the same distance. So I could say my brown ink contains both blue, red and yellow. So contains blue, red and yellow. Okay. There is, however, one substance that doesn't match with anything. So it's an unknown substance. So brown also contains an unknown substance. You also know, because the green doesn't match in the brown ink, you could also say brown does not contain green. Okay? And that would be the kind of key points that I would be saying about the colours that are in the brown ink. You are actually also allowed to say about the blue colour being the most soluble because it's travelled up the furthest. So blue is the most soluble, that would get you a mark. And you could say that red is the least soluble. Okay, but I would always start off by comparing what dots are at the same height as your first point to go to. Why was the green colour still on the start line at the end of the experiment? Well, I mentioned this before. It's not because the experiment was left too long. It would never move. The green colour was insoluble. If you've got an insoluble substance like pencil, like you should draw your start line in, the pencil line should never move. And if you've got a colour that is insoluble, it will never move. It's not because it would contain too many colours, because they would all separate out. And it's not because the green spot was too small. Right, 6.4 then. The only calculation that you've got to be able to do is an RF value. A student calculated the RF value to be 0.24. The colour moved up 1.8 centimetres from the start line. So we know our distance moved by the colour is 1.8 centimetres and our RF value is 0.24. Calculate the distance moved by the solvent front. So what I need to do then is rearrange the equation to make the distance moved by the solvent the subject of the equation. Now you can rearrange it, okay, so what you could do, if you just simplify it down, RF is distance or dot over solvent or colour over solvent. If you times by the solvent both sides, it would be RF times by solvent equals colour. Okay, so you're doing the inverse. Instead of dividing, you would be timesing it. And then to get the solvent by itself, it would be the colour. Okay, you would divide by RF. So you move the RF basically down to the other side. So solvent equals colour of your ink divided by RF. So this is the rearranged equation. What you could also do, I know physicists don't really like this, but you could put it into an equation triangle if you find that easier. RF value is distance moved by the colour over the solvent, and therefore solvent is just is your colour divided by your RF, which is what we've got here. Okay, so you can put it into a triangle if you need. So therefore your colour, distance moved by the colour is 1.8 centimetres divided by 0.24. 1.8 divided by 0.24, if you do that, would be 7.5 centimetres. Okay, question 7 then. Last question on the paper. Water that is safe to drink is called potable water. Compare how easily potable water can be obtained from wastewater and then groundwater. Now, wastewater is your sewage, groundwater is your fresh water in like lakes and rivers. Now, this is quite a complex process of treating wastewater, so if you can't remember it, go off and watch the Cognito revision video on that topic now, because there's quite a lot to it. In terms of treating them though, to make potable water, hopefully it should be quite obvious that sewage water is harder to treat, whereas groundwater for fresh water from a lake or river is easier to treat. In terms of a good compare question, try and link in the word whereas as a good comparison word to make that really obvious. So I would say, if I'm starting this off, in terms of just talking about the general overall points, wastewater contains more steps and processes, whereas groundwater contains fewer steps and processes to make potable water. So a good comparison there, linking in the word whereas. You could then also say wastewater takes longer to make potable water, whereas groundwater or fresh water is a much shorter time. So another clear comparison there. You could then just make it really obvious in your answer. Therefore, wastewater is harder to produce potable water, okay? Fresh water or groundwater is easier. So you've got some kind of comparison between the stages here and the steps. That's your kind of introduction part to it. Then you can actually dive into the detail of the differences in the processes. So I would be saying, in fresh water, there are only 3 stages. There are 2 stages really. First stage, you choose your water supply. Is it coming from a lake or river? You would then filter using filter bed. So you run it through sand and grit, and that removes the solid. And then to that fresh water, you've taken out all of the solid grit, but then you need to add sterilising agents. To kill pathogens and microbes. Now these sterilising agents can be things like ozone, UV lights, or the most common one, chlorine. You can then say about wastewater, and this is when you need to link in the Cognito clip with all of that detail on. For wastewater, yes, it's similar in terms of filtration, but we call it screening to remove the solid pieces of material. But then this is the key difference. We use a sediment tank in order to separate the water into effluent and then sludge we should remember that effluent is treated with aerobic digestion of bacteria, whereas the sludge is done and treated anaerobically without oxygen. And then it can then be put back in, or the effluent can be put back into the environment, and the sludge can be used for things like fertiliser, etc. Okay, so then you can actually start, once you've done the kind of introduction part to it, then to really start comparing and saying the similarities, but also the differences. Similarities in terms of filtering and screening, but then you've got the additional steps that you also have to know. Next part then. A scientist produced potable water from 150 centimetre cubed of salty water. Which process can produce potable water from salty water? So it's basically desalinating. Desalinate means to remove salt. Which process can do this? Okay, well, the key one is actually the first one, distillation. Hopefully you would have heated up some salty water before. The water evaporates, leaving the salt behind. And if you condense that water vapour, you get it into a different container. The salty water can then contain sodium chloride. The scientists collected 2.4 grams of sodium chloride from 150 centimetre cubed of salty water. Calculate the concentration of sodium chloride in grams per decimetre. So this is a calculation that actually normally comes up on paper 1, but they've put it here as well. Concentration is equal to mass over volume. Mass always has to be in grams, but volume, as they've asked for it here, is in decimetre cubed. What you need to remember is there's 1,000 centimetre cubed in a decimetre cubed. So in this equation, concentration is what we're finding, so we don't need to rearrange it. But your mass is 2.40. Your volume is given to you in centimetre cubed, not decimetre cubed. So you would divide it by 1,000. So 150 divided by 1,000 is 0.15. Once you then do that, you do 2.4 over 0.15, that then gives us 16 grams per decimetre cubed. And that is your final answer. That then brings us to the end of the questions on this chemistry paper 2. I hope it was useful. And yeah, remember, if you got stuck on any points, go back and watch the linked Cognito videos on that, and then try a different past paper to help you practice similar questions on it. Many thanks.